Okay, this week we're going to start with the application layer, which is our first top layer in the internet protocol stack. So let's go over the outline for today. First of all, we're going to start with the principles of network applications. Then we are going to move on to some specific and commonly used protocols at the application layer, which are, some of the applications are web, HTTP, FTP, electronic mail, and DNS. So what's our main goals in this application layer is to understand the conceptual and the implementation aspects of the network application protocols. More specifically, we're gonna, focus on transport layer service models, client service architecture, and peer-to-peer architecture. And then we're gonna, after this brief introduction, we're gonna go to details of some of the popular protocols at application level, which are HTTP, FTP, SMTP, and DNS. So what are the popular network applications? Are mostly every day we use exchange email, send and receive emails, and we do surf in the web, and we send out text messages, right? Sometimes we remotely access to and log into a server or a computer. And there are some applications that use the P2P file sharing. And there are multi-user online games, and there are some, streaming video platforms such as YouTube and Netflix and Hulu. And also one of the another popular application is the voice over IP, such as Skype and so on. And we do a lot of real-time video conferencing nowadays. And social networking is another very commonly used application. And we do web search and so on. So these are some popular network application that we utilize in our daily life. So we are, designing and developing and, network. What's our purpose in this case is to support some of the application that we just mentioned in the previous slide. So what are the, the parameters or the criteria that we should consider when we design or develop a network application? So first of all, we write such network applications that run on end systems, which we call hosts or client. And in order to support the network application, we need to provide a communication infrastructure so that our network application can talk to the network core. For instance, the web server applications, let's consider that application. So the web server software communicates with the browser software. In such case, we don't need to write software programs for the network core devices. Why? Because these network core devices, they don't run user applications, and they mostly support up to layer 3, which is the network layer. So they don't support the transport and the application layer. That's why we don't need to write software for network core devices. And application on the host allows for rapid application development and propagation. So, as I mentioned before, the end systems can support up to 5 layer, which is the application layer, top layer. And this network application, they talk to each other through the application layer level. Okay, so what are the choices for the application architectures? We have two main possible structure for the network applications. The first one is the client-server structure, and the second one is the peer-to-peer structure. Let's describe these two architectures in details, starting with the client-server architecture. So in this architecture, we have two main entities. The first one is, as you see from here, is the server, and the other entity is the clients, which can be smartphone, laptop, tablet, and so on. So, what are the main feature and function of the server? So the servers always must be on. So it's a host that always 724 that runs. It has permanent IP address, and it's usually allocated in the data centers for scaling. What about the main feature and requirements of the clients? Their main job is to communicate with the server and fetch the required data needed. So how often it can connect to the server? Intermittently, sometimes, depends on the need. So it doesn't have to always be connected. Whenever it needs to connect to servers, so it just connects. In contrast to server, the clients may have dynamic IP addresses. And in this architecture, the clients do not communicate directly with each other. So the smartphone cannot talk to another laptop, another client directly. It has to go through server. So this is one of the main requirements of the server client architecture. Let's look at the P2P architecture, the second type of structure for the network, peer-to-peer architecture. So there is no always on server in this case compared to the server client architecture. So in this case, the main feature of this architecture, each end system host can directly talk to each other. This laptop can talk to this computer, this phone can talk to this computer, and this computer can talk to this computer. So mainly there is no server, so the clients talk to each other directly without going any kind of server. So the peers, which we call peers in this case, request service from other peers. And in such request, the other peers provide service in return to the other peers. So one of the common feature of this architecture is the self-scalability. What does it mean? Each new peers, when they enter to the network, they bring new service capacity, as well as, of course, new service demands. So if you want to add yourself to this peer-to-peer network, you need to open your resources, your computing resources to the network so that the others can also take the benefit of these resources. They can utilize your computing resources, basically your computer or your smartphone. And another important thing is that we said that the peers are intermittently connected and they change IP addresses. So they don't have to always connect to each other. So whenever they need, they just connect. Compared to the server-client architecture, the management of this P2P architecture is more complex. So this is one of the main disadvantage of this architecture. Okay, so at the application layer, one of the important terminology or the concept that we should know is the process. What is the process? Let's define it. Process is a program running within a host. So basically we use this terminology for in the operating system. So what's the process? Process is basically a program running within a host. So within same host, two processes communicate using inter-process communication, which is defined by the operating system. So it's possible that you can run many processes within the same host, and all of these processes, they talk to each other through inter-process communication, and which is defined by operating system. It's also possible that processes in different hosts communicate by exchanging messages. So there, which is the more common case, the process in different hosts, they need to talk to each other, and they achieve this through by exchanging the messages. So there are two main type of the process, which we call client process and server process. What is the client process? It is the process that initiates the communications. So the client first start to request communication. So this process is called client process. The server process is the process that waits to be contacted in the server side, which we call server process. Okay, so process was one of the is one of the important concept that we should know. Another concept that we should know at the application layer is the sockets. So we define the process, which is a program that run on the end system, right? As you can see, there's a computer A and there's a computer B, and we have the application layer in the computer A, and we have the application layer at computer B. So this process in different hosts, they communicate with each other. So the process during this communication, they send and receive messages to its socket. So what's the socket? Socket is a kind of door, you can think of that, is a door between the application and the transport layer. So it push the messages from the application to the transport layer. It's the door between application and the transport layers. So sending process relies on transport infrastructure on the other side of the door to deliver message to socket at the receiving process. So when the application layer shoves out a message to the transport, it doesn't think, so it depends, it relies on the transport infrastructure. Is controlled by the application developer, and the remaining 4 layers, which are transport network, link, and physical layer, are controlled by operating system. Okay, how we manage the process address. So in order to receive messages, process must have identifier ID. The host device, as you know, has a unique 32-bit IP address. But the question is, does IP address of host on which process runs suffice for identifying the process? So in other words, IP address is enough to differentiate different processes? No, because within the same host, many processes can be run. So therefore, we need another piece of information to differentiate processes that run on the same host. Basically, to differentiate the process, we need another piece of information. And this information is additional information that we need is port numbers. So the process ID is equal to IP address plus the port numbers associated with process on the host. So when we say process ID, what's the process ID? Process ID is the IP address plus the port numbers that associated with process on the host. Okay, so let's give an example about some port numbers. For instance, it's common to use port numbers of 80 for HTTP server and 25 for the mail server. So for instance, if you want to send a message, HTTP message to this following University of Massachusetts web server, for instance, the IP address is 128.119.245.12 and the port number is 80. So the combination of these two information is called process ID in order to send a HTTP message. So the question is what the application layer protocol defines. So these are the four main things that application layer protocol defines. First of all, types of messages exchanged, whether it's a request or response. So the type of message that is exchanged is defined by this protocol. Another thing is the message syntax. So what fields in the messages and how fields are delineated. And we're gonna see each protocol has their own formats. And each format has different fields. So the protocol defines these fields and how they're filled. So another things that it defines is the message semantics. Okay, we define the fields in the format, but what are the meaning of this piece of information in these fields? And last one, this protocol defines the rules for when and how processes send and respond to the messages. So it defines how to respond and how to send the messages. You know, different types of protocols at the application layer, and some of them are, you know, public open protocols, which is defined by the RFCs, and these are allowed for interoperability. Some of the examples for this type of protocols are HTTP and SMTP. Of course, there are some proprietary protocols by the companies and so on. For instance, like Skype. Okay. The question is, what kind of transport service that application needs from the transport service? So we can classify these services in 4 categories. The first one is the data integrity. So, in other words, when you develop an application layer, uh, when you develop an application, let's say, we need to consider the following 4 services, which are very important. So we don't usually rush to write the codes. Before that, we need to come up with an architecture, as you see, whether it's a client server or is a P2P architecture and so on. Then we need to consider the following 4 services that are very important for your specific application. The first one is the data integrity. So some of the applications like file transfer, web transaction require 100% data transfer. But there are some applications like audio application that can tolerate some loss. Let's give an example. For the first application that requires 100% reliable data transfer, like a online, mobile bank and transactions. So assume that you are transferring 1,000 Turkish lira, or I don't know, let's say 1 million or Turkish lira, and this you're developing an application that support this bank money transfer, okay? And this must be 100% reliable, otherwise it's gonna be useless, and not only useless, you can get in trouble because the customer is sending 1 million Turkish lira, and because of your application, it's the 1 million is modified as a 1,000 Turkish lira. Then you're in trouble. So because you're losing 3 zeros, and so the money that is transferred, it's reduced from 1 million to 1,000. So this is not tolerable. So this is not acceptable in this application. So, but there are some other applications like audio application. You're developing a kind of VoIP application. So the voice quality can be tolerated in this case, or the delay in this case. So therefore, for your specific application, you need to satisfy the data integrity requirements. If it's a money transfer, you have to be 100% reliable. If it's kind of VoIP application, then some of the loss can be tolerable. So the second one is the timing requirements. So what are the timing requirements for your application that you're going to develop? Does it require low delay, ultra low delay, and so on? So you need to be very specific, even if you can provide a number which would be better. So some applications such as voice over IP, interactive games require low delay to be effective, right? Specifically for the online games, these timing requirements are very strict. So assume that you are playing table tennis, you're in Istanbul, and there's another of your friend in Africa. So when you hit the ball, it has to be on the other side, which is in Africa, within maybe milliseconds. If this delay is very long, then your friend in Africa is not able to play the table tennis, because table tennis game requires very restricted time. Actually, it requires very low delay to be effective, to play a good game. But there are some applications such as email, it doesn't require that much low delay. You send an email, it can, reach to your friend in Africa within minutes, 5 minutes, 10 minutes, which is not that much important. So compared to the online games. So your application basically define your timing requirements. Another important parameters that we need to consider is the throughput requirement of your application. So some of the applications, such as the multimedia, require minimum amount of throughput that you need to provide. Like, you are watching a video or you are watching a movie over the Netflix and so on. So you have to provide a minimum bandwidth so that the customers can watch this movie, effectively. But there are some other applications which we call elastic apps. They use of whatever throughput that you provide. So they don't have any stricted kind of requirement in terms of the throughputs. Okay, so throughput, in other words, the bandwidth is very important. So you can come up with a very, kind of fancy application that you develop. But if you skip this throughput, which is kind of a bandwidth of your backbone or backhaul, whatever is the data rate of your internet, your application may not work properly. So you have to be careful when you define the throughput requirement of your application. The last one in this category is the security, of course. So the application that you provide should be secure. Otherwise, people will be reluctant to use your application. So there are different, methods to provide security in terms of encryptions and data integrity and so on, at different level even. Sometimes we provide some security, apply security levels at the application layer, sometimes network layer, sometimes the physical layer, and so on. So whatever method that we select, our application must provide a security service so that your data that is gonna be exchanged needs to go through a secure channel. So these are the 4 important transport services that you should consider prior to developing an application. And you have to be very in terms of these parameters. Okay, let's give some examples for these transport service requirements in terms of popular applications. For instance, the file transfer. You transfer file using the FTP, for instance. So the data loss requirement in this case, the data integrity, we cannot accept any loss. So if you're transferring like a Word or the PDF document, whatever information in that document, PDF or Excel or Word, it has to be reserved, right? We don't accept any kind of, even one, ladder to be lost. One piece of information cannot be lost when you transfer a file. The throughput can be elastic. We don't have much strict requirements in this case. It can be transferred within 1 minute, 3 minutes. It's okay, but no loss, okay? No data loss. Time sensitive, no, because as I said, it depends on the throughput, of course, and this will decide on the time that is transferred. So we don't have any kind of specific time requirements for this application. It can go, as I said, after 3 minutes. As soon as the whole piece of information is transferred, that's fine. So another application is the email. You're typing an email to your friend in the, so this message has to be transferred to your friend email account without any loss. We cannot accept loss in this case because you're sending a very important messages, and this message shouldn't be lost, any piece even. And the throughput and time sensitive is like file transfer. Depends on the bandwidth of your network infrastructure, and it can go anytime, so it doesn't have to be within millisecond or 1 second. It can go within minutes and so on. Web documents is another applications. But let's look at some other application like real-time audio video applications. These are loss tolerant. So some piece of information can be lost. I'm talking over the real-time audio voice chat. So when I say hello, okay, some of the information can be lost. And the throughput, there are some minimum requirements, like for the audio is between 5 kilobit per second to 1 megabit per second. And for video is like between 10 kilobit per second to 5 megabit per second. And these real-time audio video application they are time sensitive. It has to be within hundreds of millisecond range. So let's assume that you are talking your mother and you're saying salam anne. And after saying that, this goes to your mother phone. Let's say after 1 minute. Does it acceptable? No. So it has to go right away within a time that the human ear cannot, differentiate these laws, basically. Another application is the stored audio video, which is has the same requirements like real-time audio video as above. Interactive games, they are loss tolerant. Sometimes 1 pixel can be lost, which is okay, still I can play the game. And most of the games, they require some minimum throughput, like few kilobit per second. And more importantly, the interactive games, as I mentioned before, they are time sensitive applications. So we need to provide this data exchange within few seconds. Like in the table tennis game, I'm hitting the ball in Istanbul, and my friend on the other table side, which is reside in Africa, it has to receive this ball within maximum few seconds. Otherwise, you cannot play the game effectively. The last example in this case is text messaging, like WhatsApp or SMS, whatever. So we don't accept any loss because you're typing a message, text. This completely has to be transferred to the other side without any loss. And the throughput can be elastic. There's no any strict requirements or limits in this case. Time sensitive, no. Yeah, so it's okay if your text message reach to your friends, your destination within seconds, so minutes, it doesn't matter. So it's okay. And then you can increase the example list but these are some popular applications that we use commonly. Okay. Internet Transport Protocol Services. So what are the transport protocols that we use below the application layer, which is the transport layer? So there are two common service in this case, which is the TCP service and the UDP service. So let's compare these two services to each other. Let's start with the TCP. It provides a reliable transport between the sending and the receiving. So the TCP service support the reliable data transfer. And it has a flow control feature. What's the flow control? So the flow of the data sometimes may overwhelm the receiver side. So that's why TCP has a flow control that limit the standard so that it will not overload the receiver. Another important feature of the TCP service is the congestion control. You know what's the congestion? Congestion is the kind of traffic that we also experience in our daily life, in the traffic in the street. So similarly, in the network, we have also the congestion. So in this case, the TCP service, limit the standard when the network is overloaded. So it controls some parameters so that to avoid or to mitigate the congestion in the network, the traffic in the network. Another feature of the TCP service, it doesn't provide any timing, so it doesn't guarantee minimum throughput or timing or security. And TCP is a connection-oriented protocol service because its setup required between client and server processes. So first of all, it set up a connection between the client and server processes. Then it start to exchange the data. Okay, so these are some important features of the TCP service. Let's go over the UDP service. Compared to TCP, UDP is an unreliable data transfer. It works based on the best effort strategy. And it doesn't provide the other features that TCP provides, such as reliability, flow control, congestion control, timing, minimum kind of throughput guarantee, security, or connection setup. Is a connectionless protocol. But, despite this, UDP also is useful in some application that we are gonna learn later on. Okay, so let's look at some application and their respective underlying transport protocol. The application is email, electronic mail. The application layer protocol that it uses is SMTP, and the RFC code is 2821. And the underlying transport protocol at transport layer is TCP. Remote terminal access is application. One of the application layer and most common one is the telnet. The code is RFC 854, and the underlying transport protocol is TCP. Another application is web, and its application layer protocol is HTTP, and the RFC code is 2616. And the underlying transport protocol is TCP. The file transfer is our application. The popular application layer protocol is the FTP, and the standard number is RFC 959. And it uses also TCP as a transport protocol. Streaming multimedia, there are different cases in this application. Like YouTube, it utilizes HTTP. There are some RTP protocol, and some of them use TCP or UDP. Internet telephony, voice over IP, application layer protocol is SIP, RTP, or some proprietary like Skype protocol. It can utilize TCP or UDP depend on the application. So as you can see, there are application layer protocol and their transport layer protocol depend on the application. So if you remember TCP, we said it's originally is not designed that support the security. But nowadays we are using kind of secure TCP. How do we achieve this? So this TCP and UDP, as you see, they don't have any encryption, the original one. So, and they send a clear test password into the socket, and then they receive on the other side. So we can secure the TCP at the application layer using the SSL. SSL, what's the SSL? It provides an encrypted TCP connection, data integrity, and endpoint authentication. So why we use SSL is to provide an encrypted TCP connection to satisfy data integrity and endpoint authentication. So the application at app layer, they use the SSL libraries which talk to the TCP. And we're going to see later on the details. Okay, these are the main things that you should know about the principles of the network applications in terms of architecture and their requirements. To summarize, so we have two types of network architecture that we mentioned. The first one is client-server architecture. The other one is P2P, peer-to-peer application. And we went over their requirements and underlying protocols that are used. And there are four main transport services that we need for the application, which are data integrity, timing, throughput, and the security. So we should determine these requirements when we develop an application. Okay, so now after this introducing these fundamentals of the network application, let's move on some specific examples. And you mostly know these applications. The first one is web and HTTP. So website is one of the common things that we use in the internet. So a web page consists of objects, right? And this object can be like HTML file, JPEG image, Java applet, some audio file, and so on. So web page consists of, first of all, the base HTML file, which includes several referenced objects. And each object is can be addressed by URL. For instance, let's look at one of the example for URL. This is one of the example, www.somedepartment/somedepartment/picture.gif. So the first part is called host name, like www.someschool.edu. For instance, in our case, www.gtu.edu.tr is our host name. And the remaining part is called path name, like computer engineering department /pic.picture.gif. This is called path name. So let's start with the HTTP. It stands for Hypertext Transfer Protocol. It's a web's application layer protocol that we use at the application layer. It works based on client-server model, and the client has a browser that requests, receives, and render displays the web objects that is fetched from the server. Of course, using the HTTP protocol. The server, what's the main function of the server? Web server sends objects in response to the client request. Let's watch the animation together. So here we have a server that runs Apache web server, and we have a desktop PC running the Firefox browser. And on the other hand, we have another client, which is iPhone, running the Safari browser. So when you want to reach a website through the HTTP, first of all, the client requests by sending the HTTP request to the server, and the web server sends back objects in response to this request. This is the same for the smartphone. So it's basically smartphone also requests the objects or the web page through the HTTP request, and then server sends back the objects or whatever files in response to this request. Okay, so let's look at the main feature of the HTTP. So in this TCP, the client initiates the TCP connection by creating the socket to server, such as, in this case, it's port 80, and the server accepts this TCP connection from client, and then once the connection is set up, the HTTP messages are exchanged between the browser and the web server, which we call browser in this case is an HTTP client. The web server is the HTTP server in this case. So it's a three-phase kind of communication. First, we set up the connection, and then we exchange the HTTP messages. Once we are done with the data exchange through the HTTP messages, the last phase is to close the connection. So the TCP connection is closed after you are done with your data exchange. HTTP is stateless. It doesn't keep any states. Server maintains no information about past client requests, because the protocols that keep the states are really complex. Why? Because all the past history, the states of the clients, all these requests must be maintained and must be stored. But in case of crashes, then you need to kind of reconcile all these different information. So that's why the protocol are. But in our case, HTTP it's stateless, which doesn't support state. Doesn't keep any state of information. So we have two types of mainly HTTP connections: non-persistent versus persistent HTTP. What is non-persistent HTTP? We said first we set up a TCP connection, then we start to exchange the data between the HTTP server and HTTP client. during this exchange, at most maximum one object can be sent over this TCP connection. Then the connection is closed. So that means in non-persistent HTTP, we are allowed to send just one object over one TCP connection. If you are downloading multiple objects, then it requires multiple connection. You know, the number from the previous slides, we have to open the connection, we have to send one object, then close the connection. For the second object, we need to open a new connection, TCP connection, then exchange this object, then close the connection. And for third, you're gonna do these same steps. So in summary, if you're downloading multiple objects, you need to run multiple TCP connections in non-persistent HTTP case. To address to this issue, you know, persistent HTTP is developed, which allow us to, you know, send a multiple objects over a single TCP connection. So in these HTTP connections, we are allowed to send the multiple objects in just one single connection. These are some, you know, example for the non-persistent HTTP. I'm skipping, just we mentioned about that. So after sending one object through a single connection, you have to do all these 5 steps for each objects. Let's look at non-persistent HTTP in terms of response time, or you may say delay. So we have a client here, a computer, and we have a server here. According to TCP protocol, the client initiate TCP connection. It send a request, and then server respond back to the client, let's say positively. So it accept the connection, is open the connection, but this time is called RTT. Time for a small packet to travel from client to server and back is round trip time. So it's first the time from client to server and back from server to client. So this total time is called RTT, round trip time. And then after opening the TCP connection, the client start to request specific files objects, and then it send a request, and server, it takes time to transmit this requested file, and then the file received. So what is the total response time for the non-persistent HTTPs? As you see, is one RTT here plus another RTT, 2 RTT, and plus we have time to transmit time, file transmission time we call it. So this is the total response. So total response is equal to 2 round trip time plus file transmission time. Let's look at the persistent HTTP. So what is the issue in non-persistent HTTP case? It requires at least 2 RTTs per object. So for each object that you request from the server, it requires 2 RTTs time, and plus some operating system overhead for each TP connection. But there's some other solution for this, to addressing this issue, such as, you know, opening the parallel TCP connection. which is done by the browsers. So the browser sometimes open this parallel TCP connection to speed up this this process in order to fetch the referenced object from the server. Persistent HTTP, how it addressed this issue. In case of persistent HTTP, the server leaves TCP connection open after sending the response. So the subsequent HTTP messages between the client and server are sent over this open TCP connection. So server doesn't close right away after a single object transmission. It leaves open, and multiple HTTP messages can be sent over this open connection. So what is the response time in this case is as little as 1 RTT for all the referenced objects, is approximately equal to 1 RTT compared to 2 RTT in case of non-persistent. Almost 50% response time is reduced by utilizing the persistent HTTP. You are very familiar about this message and formats, in ASCII formats. So there are two types of HTTP messages, request and response, and these are some example which I'm skipping quickly. This is the general format of the HTTP request messages. It has we talk about the fields, method, URL, version, header field name, value, blah, blah, entity body. Some uploading form inputs. There are two types of methods, post method and URL methods. So the input in case of the post method is uploaded to the server in entity body, whereas in the URL method, this is uploaded in the URL line, as you see. Method types HTTP 1.0, 1.1. Some as an example for the HTTP response message. And these are some popular HTTP response codes. It appears in the first line in the servers to client response messages. Some of the one that we come across, I think one of the most popular one is 404 not found, means requested document not found on this server. So you are requesting a document from a server, but somehow this document is removed or not found on this server. 200 means okay. Request succeeded, requested object later in this message. The code 301 is moved permanently. So the object that you requested is moved sometimes to a new location, and they can provide a new location for that. 400 is a bad request. Request message not understood by server. 505 HTTP version not supported. These are some sample codes of the HTTP response. You can try out, some HTTP basic commands for yourself using the telnet. You can type get, and so on. Okay, in this kind of application, web and HTTP, we use a lot, which shows us the user server state. Nowadays, many websites, use the cookies, and cookies has 4 main components. Cookie header line of the HTTP response message, cookie header line in the next HTTP request message, cookie file kept on user host managed by user browser, and backend database at the website, where each of these cookie entries this is the database at the back end. Why we use cookies? For example, the Susan always access internet from PC at home. It visits a specific e-commerce site for the first time. So when initial HTTP request arrives at site, this website creates two things. One of them is the unique ID for that specific client, and it entry in the backend database for ID. So it enter this ID into this backend database. Let's look at this by animation. So we have a client here which use PC to access internet, and we have this server which is a www some electronic commerce, let's say, website. As you see, the browser has a cookie file which keep the cookies ID. Like previously it keep another website for which is an eBay, and the ID is 8734. But let's assume that Susan now access first time to Amazon server. As you know, it used the usual HTTP request message, and Amazon server create an ID for that specific client, which is 1678. And then Amazon server has a backend database for these cookies, and it create the entry, and then put this ID into the database. And then server, it respond with the usual HTTP response, but by putting this cookie ID in the header line, and it set cookie. And then the client side store this specific ID for the Amazon website, which is 1678. And then usual HTTP request to get some information, and then cookie specific action is done by accessing the database, and then server respond back to the client using the HTTP response message. Let's say after 1 week, the Susan wants to reach to the Amazon again, but now the cookie ID is sent by HTTP request messages, and then the Amazon server is going to take an action based on this cookie ID by accessing to the backend database, and then server responds to the client using the HTTP response. So this way it speed up some of the action using the cookies. What cookies can be used for? So the intention to use cookies are for the authorization, for the shopping carts, for recommendation to other information or products, and user session state. So, but there are some kind of concern about using the cookies, because cookies may violate your privacy. So the cookies allow or give a permission to the site to learn a lot about your personal information. So you may provide your name or email address or some personal data to the to the websites. So these are some concern about the usage of the cookies. Okay, so another concept about the web application is the cache or web caches, or we call it proxy server. What is the main reason to use this proxy or caches is to satisfy the client request without involving the origin server. Assume that you have a very on-demand origin server which is demanded a lot. In order to reduce the traffic of this server, we set up a proxy server so that we can reduce the load of this main server. User sets browser, and then web accesses via cache. And then browser sends all HTTP requests to this proxy server. If the object in the cache, the proxy server returns object. If not, cache request object from the original server, then returns object to the client. Let's look at the animation together. So user set the browser, and browser ask request. Browser sends HTTP request to the cache or proxy. If the object is in the proxy server, then it sends right away. If not, then of course it needs to get this object from the origin server, main server. So once the proxy server receives this object, it returns object to the client. Okay. So in this case, the proxy or the cache acts like both client and server. Why? Because it acts like a server for original requesting client, and it acts like client to the original server. And typically this kind of proxy server is installed by your ISP, internet service provider, like university, company, and so on. We just mentioned at the beginning of this previous slide why we should use web cache or web proxy server, because it reduced the response time for client request, and it reduced the traffic or the load of the institution's access link, the main server. And so it effectively, kind of provide a content to the client, in timely manner. Okay, these are the main reason why we use the web caching. Some example, which I'm skipping. These are some conditional get for the HTTP. Okay, so let's have a 10 minutes break.